No matter what kind of problems are you solving, whether it's in mathematics or in some other area, there is one skill that will make you more effective in solving any kinds of problems. That is a skill of comparing different ways of solving problems and then choosing the one that fits you the best. And nothing trains this skill better than mathematics. So I decided that my channel will also be about different ways of solving different simple problems. You're about to watch the mathster at work. I bet that if you're watching this video and you're older than 12 years old, you have solved many quadratic equations in your life. That is a very simple and basic problem of mathematics, and it seems like we know everything about it. But if we dig deeper, we realize how much more there is to say. So let's talk about different ways of solving a quadratic equation. First of all, there is a method of completing the square. That is a basic, widely known method, so we won't go into details here. We should think of a number such that there will be a perfect square at the left-hand side. If there is x squared minus 4x, then what I need is plus 4, so this is a perfect square. But instead of plus 4, I have minus 5 here, so in order to not change anything at the left-hand side, I should subtract 9. And that all equals to 0. Or I could have just added 4 to both sides of the equation, so that's what I would get. Now, I have x minus 2 squared at the left-hand side and 9 at the right-hand side, which means that x minus 2 equals plus or minus 3, so x is either 5 or minus 1. The quadratic formula, which again I'm sure everyone is familiar with, this method is basically just completing a square, but instead of making a quadratic equation to a perfect square, which could sometimes be troublesome, we just use formula that always works. There are two steps. First, we evaluate the discriminant. The discriminant is that expression under the square root. For our first example, the discriminant equals 25 minus 4 times 2 times minus 12, which is equal to 25 plus 96, or 121, or 11 squared. And here's a good tip. You will be making less mistakes if you always end your discriminant as a square. And if the discriminant is positive, as in that case, then we have got two roots, which we can find using that formula. X equals minus 5 plus minus square root of 11 squared is just 11 over 2a. Another popular mistake is forgetting that we divide by 2a and dividing just by 2. That happens because we're used to solve quadratic equations with a square coefficient equal to 1. And here we've got 2 there. So we have minus 16 over 4 or minus 4 or 6 over 4, which is 3/2. If the discriminant is negative, as in that case, 25 minus 4 times 2 times 12, which is 25 minus 96 and is obviously negative, we have got no roots. The shortest way to express that is to just write down an empty set of solutions. And third case scenario is a case when we have got the discriminant which is equal to 0, as in that case, minus 28 squared minus 4 times 4 times 49 is just basically equal to 28 squared minus 4 squared times 7 squared, which is 28 squared as well. So that's 0. And in that case, we use the same formula, but since that square root is 0, we just divide minus b by 2a. So the answer is minus b, or 28, over 2a over 8, or 7/4. Why does that formula work? As I said in the beginning, a quadratic formula method is basically just completing a square. Let me show you that. If I have got a quadratic equation which looks like that, then by multiplying it by 4a, I get 4a squared x squared plus 4abx plus 4ac equals 0. Now we have got to add b squared to both sides of equation. You'll see why in a second. We have got 2ax squared, which is just 4a squared x squared, plus 2 times 2ax times b, which is just 4abx, plus b squared equals b squared minus 4ac. So I guess I should have said that I add b squared and then subtract 4ac. That's why we don't have 4ac at the left-hand side, and we have got minus 4ac at the right-hand side. Now we've got an equation which looks like that, 2ax plus b squared equals b squared minus 4ac. And that expression looks familiar. That's the discriminant. And it's equal to a complete square. And now we understand why the equation has two roots when the discriminant is positive, one root when it's equal to 0, or no roots when it's negative. So for that equation, we have got 2ax plus b equals plus minus square root of b squared minus 4ac, which implies that x is minus b plus minus squared root over 2a. And that's how we've got that formula. And we should also say that every transformation that we have made here is possible only for a which is not equal to 0. And our next method is factoring. This method is pretty common too. And factoring is the process of finding two expressions whose product is equal to the quadratic equation. So we just factor the left-hand side into a product of two linear expressions. And in order to do that, we have to find two numbers whose product is equal to minus 6. Let's say it's minus 3 and 2. But that doesn't work because minus 3x plus 2x is minus x. So if we were to open that parenthesis and multiply both expressions by each other, then I would get minus 3x plus 2x or minus x, among other terms. And I have got plus x here, which means that I have to obtain minus 6 as a product of two other numbers, let's say plus 3 and minus 2. And that actually works, because now if I multiply these expressions by each other, then what I've got is x squared plus 3x minus 2x minus 6, which is equal to that. So factoring a quadratic equation is just an attempt to reverse engineer multiplication of two linear expressions. So that equals to 0, and once we have factored the equation, we can set each factor equal to 0. So x plus 3 equals 0, or x minus 2 equals 0, which means that x is minus 3 or 2. Vieta's formula, we still think about the product and the sum of the roots, and then try solving that system of equations. So in that case, I have a system of equations x1 plus x2 equals 5 and x1 times x2 equals minus 24. And I think of two numbers whose sum is 5 and product is minus 24. And it looks like 8 and minus 3 work here. Notice that Vieta's formula only works for the discriminant which is positive. So it's worth finding the sign of the discriminant first, at least in your mind. In that case, we would have minus 5 squared minus 4 times minus 24, which is 25 plus 96, which is obviously positive. Now let's move to methods of solving quadratic equations that are not so widely spread. Coefficients property number 1 works like that. If for the quadratic equation ax squared plus bx plus c equals 0, equality a plus b plus c equals 0, or in other words, sum of the coefficients is 0, then the roots of this quadratic equation are 1, always 1, and c over a. For example, in that case, we have a quadratic equation for which a equals 13, b equals minus 40, and c is 27. And we see that a plus b plus c is equal to 13 minus 40 plus 27, which is obviously 0. So that property works. And I can say that the roots are 1 and c over a. x1 equals 1 and x2 equals 27 over 13. That is a great way of solving quadratic equation because I can basically do it in my mind. All I had to calculate here is that 13 plus 27 equals 40, and here's minus 40. And we can see that solving that equation using classic methods would be a big problem because, first of all, we have to deal with big numbers. We would have to multiply 13 by 27, raising minus 40 to a power of 2, which is not that big of a problem, but still. And using that property, all I had to count was 13 plus 27 equals 40. And that's it. And I had the roots right away. The only disadvantage of that method is that it works very rarely, because we don't have that much equations for which a plus b plus c equals 0. But here's why we should care about that property very much. The trick is that problem compilers use that property to come up with equations. For example, if you asked me to come up with a quadratic equation with big bulky discriminant and complicated roots, I would give you something like that. 2022x squared minus 2023x plus 1 equals 0. Solving that using classic methods would be a suicide. But I can see that property 1 works, so the roots are 1 and c over a, 1 over 2022. So it turns out to be a no-brainer. Let's move on to property number 2, which looks very similar. If for the quadratic equation equality a plus c equals b is true, then the roots are minus 1 and minus c over a. Notice the difference between these two properties. In property 1, we had a sum of coefficients which was equal to 0. And in property 2, we have a plus c equals b. Or in other words, a minus b plus c equals 0. So here clearly 27 plus 26 equals 53, and the roots are minus 1 and minus c over a, so minus 26 27ths. And that's the answer. And again, it took me a couple seconds to solve that equation. And if I had to evaluate the discriminant, I would have to square 53 and then multiply 4 by 27 by 26, which is time consuming and annoying. Moving on to the property number 3, and if for the quadratic equation equality AC equals B minus 1 is true, then the roots are minus 1 over A and minus C. So using that property requires dealing with the product of A and C. And we can see here that 9 times A equals 73 minus 1. So AC equals B minus 1 is true, which means that the roots of that quadratic equation are minus 1 over A and minus C, or in other words, minus 1/9 and minus 8. Now, why exactly does it work? We can prove that it works using the discriminant again. The discriminant is b squared minus 4ac. And if ac equals b minus 1, then it's b squared minus 4 times b minus 1, or b squared minus 4b plus 4, which is equal to b minus 2 squared. And now the quadratic formula gives us x equals minus b plus minus b minus 2 over 2a, which is minus b plus 2 over 2a, or minus b plus b minus 2 over 2a. And in that case, we have got minus b plus 1 over a, whereas here we have got minus 2 over 2a, or minus 1 over a. And finally, since that is equal to minus ac, then we have got minus c here. And here are the roots of the equation. And the property number 4 looks similarly. If for the quadratic equation equality AC equals minus B minus 1 is true, then the roots are 1 over A and C. In that case, I've got 11 times minus 5 equals minus 54 minus 1, which means that the roots are 1 over A, or 1/11, and C, or just minus 5. Here's the answer. Now, these 4 properties work rarely, as we said, unlike our next method, which I call transfer method. In that method, we are basically transferring coefficient A to coefficient C, and instead of solving that quadratic equation, we solve quadratic equation which looks like that: y squared plus bx plus ac equals 0. And that method is helpful because we always have 1 here, which is very useful. We just have to remember that the roots of the initial equation are a times smaller than the roots of the equation that we've got when we transferred a to c. So, in that example, instead of solving that equation, we can solve an equation y squared minus 41y minus 42 equals 0. I've got minus 42, transferring 6 to minus 7. 6 times minus 7 is minus 42. Now the roots of that equation are minus 1 and 42. And I've got that result from the coefficients property number 2. And since the roots of the initial equation are a, or 6 times smaller than the roots of that equation, then my answer is x equals minus 1 over 6, or x equals 7. And that is the transfer method, which again is very useful because we have got 1 here. Now another method which is used quite rarely too, but is still worth our attention, is introducing a new variable. In that equation, I noticed that 338 is 2 times 169, and 169 is 13 squared. And I have got 13 here. 39 is 13 times 3. So I can rewrite this equation as 2 times 13x squared plus 3 times 13x plus 1 equals 0. And if we set 13x equals t, then 2t squared plus 3t plus 1 equals 0. And roots of that equation are pretty obvious. I'm going to use property number 2 again, because 2 plus 1 equals 3 here. So the roots are minus 1 and minus 1/2. And coming back to a variable x here, I've got x equals t over 13, which gives me the answer x equals minus 1 over 13, or minus 1 over 26. And our final 11th method of solving quadratic equations is solving a homogeneous equation. Now actually that is not a homogeneous equation as per definition, but still we can use the method here. We have to notice that 726 is 121 multiplied by 6, and 121 is 11 squared. So if we divide both sides of that equation by 11 squared, then what we've got is x over 11 squared minus 55x over 11 squared plus 726, which is 11 squared times 6, over 11 squared, which is equal to 0. Now I see that it is x 11th squared minus 5 times x 11th plus 6, which is equal to 0. So what I've got is a quadratic equation with respect to x over 11. I can introduce a new variable here if I want to, but I just want to solve that using Vieta's formula. So I have to think of two numbers whose sum is 5 and product is 6. Obviously, these numbers are 3 and 2. So we've got our answer as x equals 33 or x equals 22. What do you think about this video? Did you learn something new? Maybe there is a method that you know that I missed. Write down in comments. Consider subscribing to my channel, and if you want to learn about solving problems with parameters, the link to my Udemy course will be in description. Thank you for watching this video and dare to know.